So, last class we were discussing dislocation intersection, we looked at 4 examples, and next we have we said we will look at some more aspects of these intersections. So, what are these aspects? We want to define whether these steps are jog or kink. We want to define whether these are screw or edge, and we want to find out whether they are glissile, which means they allow movement or they move themselves, whether they are movable, or sessile, not movable. Okay, so, let us come back to our different cases. What do we see over here? Over here we see in this particular one there was no visible step formation. So, we can ignore this one. Over here what do we see? Over here we see that there is a step that has formed, and this has led to the displacement of the slip plane from here to here. So, this is no more in the same slip plane. So, first thing that we can say that this is a jog. So, the step here is a jog, and is it a edge dislocation or screw dislocation? So, this is the Berger vector which remains perpendicular even at this point. So, it is a edge dislocation. We will come to the glissile and sessile part. Actually, we have already discussed, if you remember, but we will describe it in more detail later on. So, here now let us come to case 2. So, here what we see, the step is formed and it is in this plane, the plane on which it was moving. Here also a step is formed, and this step is also allowed the dislocation to remain in the same slip plane. Therefore, the two of these must be kinks. Moreover, what is the Berger vector? So, you see that both of them Berger vector were parallel. Therefore, the step that is formed over here, this step is parallel to this Berger vector, and therefore, it is parallel to this Berger vector, which would mean this is a screw dislocation. Here line vector is parallel to the Berger vector. So, both of these are kinks, and in fact, we should know from what we discussed earlier that this will lead to a screw dislocation. So, let us get to the step 3, case 3. So, first let us look at the simpler one, which is the edge dislocation. So, here the edge dislocation, as you can see, it has moved away from the plane. So, clearly it is a jog, and if it is a jog, then by default it has to be a edge dislocation. For a edge dislocation, the jog leads to edge dislocation. What about this screw dislocation? So, this is where, when I said that it depends on what particular, where I am drawing this ledge. Now, the way I drew this ledge, it means that this is the slip plane for this. So, this is the slip plane, and this has moved it away from the slip plane, and therefore, this one is a jog. And what is the character? The Berger vector here is edge, perpendicular to the line vector. So, it is a edge dislocation. So, in both these cases we are getting jog and edge. Now, what do we get over here? So, here we have not defined any particular direction or ledge. So, we will not be able to say whether it is jog or kink. So, it will depend on a specific case, but if we assume that this particular plane is let us say this is the so if we assume that this is the slip plane for this, then perhaps we can say that this is a kink because it is in the same plane. So, let us say this is kink, and it is assuming that it is this particular plane, and if it is, and in the screw dislocation, whether it is a jog or a kink, it will always lead to edge dislocation. Now, here this we know already that it was moving, this particular screw dislocation, this was moving in this particular plane, which would mean that this particular one has moved away from the plane, and therefore, it must be a jog. Now, if you go back and actually we described it a little different, we said this dislocation is moving, and if that is the case, then we will have to revisit what we said over here, or we can say that this dislocation was moving, in which case we can stick with what we have described. So, for this particular plane is the slip plane, and after the step formation it has moved away from the slip. So, this is jog, and we are assuming that this remains stationary where it is in one of its slip plane, and therefore, this particular step has formed in the slip plane and it is a kink. So, for screw dislocation we get a edge dislocation in both the cases, and for edge dislocation when we get a jog it is a edge, when we get a kink it is a screw. So, we can let us summarize it now what we see in the table over here. So, let us say we have dislocation line 1, we have dislocation line 2, and we are looking at case 1. So, in the first case we are talking about 2 edge dislocation. So, let us first write that down. This is 2 screw dislocation, and what we obtained was that in this particular edge dislocation 1, what we obtained was a jog which has to be edge. In this particular one the step formation was in the line. So, it does not apply to this. So, that is case 1. Case 2 we had again 2 edge dislocation. So, first mark that edge dislocation line, and in one of the cases in the dislocation line 1 what we obtained was kink, and when it is kink in a edge dislocation the character is screw character. For dislocation 2 in this particular case we saw that it was also a kink and hence a screw character. Case 3 we had 1 screw dislocation and 1 edge dislocation. So, we had dislocation 1 was edge and dislocation 2 was screw dislocation. So, the edge dislocation we saw obtained jog which has to be edge, and for the screw dislocation assuming the given slip planes we say that it is jog and edge. So, I will put a star mark over here because this is to be remembered that it depends on where which particular, because there can be several slip planes and just a stationary dislocation cannot describe where is the slip plane, while in a edge dislocation even a stationary dislocation can describe what is the slip plane. So, that is why here assumption is necessary which one you are describing as the slip plane. So, I have put a star mark over here. Case 4 we had 2 screw dislocation, and again depending on the assumption, one of them we do not need to make the assumption, which is for 1. For 1 we do not need to make the assumption because we are assuming that it is moving in this particular plane. So, we know that it is moving and so its slip plane is described and it is necessarily a jog. So, for screw dislocation 1 it is necessarily a jog which means edge, and for the 2 we have to assume a certain plane. So, again we will put a star mark, but assuming that it was perpendicular to the direction of the other dislocation. So, it forms a step in the direction of the slip plane in the plane. So, it forms a kink and edge character, and I will again put a star. Star means slip planes are assumed. For other we do not need to assume slip planes. Okay. So, now the next question is whether glissile or sessile. Now, if you remember from our discussion, there was the steps that are formed whether the kink or jog in a edge dislocation, it is always glissile. in a screw dislocation, one type of step is glissile, the other type of step is not glissile, or what is called as sessile, not movable. And what is that? The one when we have jog. When a jog is formed, it forms a edge dislocation which remains confined to a particular plane, and then it cannot move in the same direction as the slip direction, and therefore, it pins down the dislocation, and therefore, it is a sessile dislocation or a sessile character, it is sessile in nature. So, here we will also put glissile, or more simpler is to say which one is sessile. So, wherever there is a screw dislocation with jog character, it will be sessile. So, I will write S. So, here it is S, and for glissile I will write G, meaning it will move. So, these two are sessile and all the remaining ones are so here also sessile, and all the remaining ones are glissile. So, I will not mention it over here, but it by default you should understand that the rest are glissile. So, whenever something like this forms, a jog forms in the screw dislocation, it will be sessile and it will lead to pinning of the boundaries, and in other words also mean that somewhere it will add to increase in the strength of the material, and the sessile dislocations would cause more intersection of dislocations and hence more generation of such sessile parts, which will add to the strength of the material. So, there are from this summary we can again note down some important steps. What are the important or not important steps, but some important takeaway messages. Screw dislocation step always edge, yeah, right. We saw that whether you are using whether we get a kink or a jog, this part we saw it I think 2 lectures back, whether it is a kink or a jog, it will always be edge dislocation. And if we are writing this, then we also need to write that for edge dislocation, jog is edge and kink is screw character. Another as important aspect is that edge dislocation step are always glissile. There may be some particular cases when there is a jog in the edge dislocation, it may not be in a desirable slip plane, but and you may need additional to move it, but it will not be sessile like the jog in a screw dislocation. For now we will say that edge dislocation steps are always glissile, whether we are talking about jog which is edge or kink which is screw. What are the other important takeaway messages from what we have seen today? That edge dislocation give rise to glissile step that can move conservatively. So, meaning of a sessile or glissile is also that when it is glissile, it would move, it will be able to move conservatively. When it is sessile, then you need thermal activation, it will have to climb to be able to move, as we will see in few more when we look about other kinds of jog which are called super jogs. But before that, let us summarize what we have learned so far. So, in edge dislocation we get glissile step that can move conservatively. On the other hand, screw dislocation, this is the most different in nature, in that screw dislocation jog which is edge character, not with edge, whenever it is screw dislocation step, it will always have edge character, whether jog or kink. So, screw dislocation job is sessile can still move forward. Remember that it's sessile does not mean it cannot move forward. It can move forward only by non-conservative process. Which requires stress and thermal activation. So, stress is anyways necessary, but along with stress you need thermal activation. So, in other words it is temperature dependent. So, these are some important take home message from the intersection of dislocation and the steps which are jogs and kinks. Now, let us look at what we were talking about, non-conservative motion of these sessile edge dislocations that are formed in jogs that are formed in the screw dislocation. So, let us say we have a dislocation line like this where steps have formed, and these are the screw dislocation part, and these steps whether jog or kink should be edge in character. But since we are talking about jog, so these are jogs, because we are interested in what happens to these jogs. Why do, if they are sessile, non movable, how do they influence? So, we will look at this. So, these are the screw dislocation and this is the edge dislocation part. Now, if the dislocation motion is taking place in this particular direction, so let us say this is the direction of motion, and what will be the Berger vector. Now, that we are talking about dislocation, so let us also describe what will be the Berger vector. It has to be parallel to the screw dislocation. So, the Berger vector will be like this, and which way would be the resolved shear stress? Resolved shear stress will have to be either like this or like this. The resolved shear stress, you remember, whenever it is causing the motion, we have to have a resolved shear stress along the Berger vector. So, we must have resolved shear stress along the Berger vector. It may be in this direction or in this direction depending on whether it is moving forward or backward. So, what will it lead to? It will lead to a motion like this. Over here, this is the slip plane for the screw dislocation, and this is one plane. So, all of them are in different planes, as you can realize. So, this is one plane, this is another plane, this is still another plane, and all of them are moving, but this part is sessile, it is not moving and it remains pinned over there. So, you can see a larger stress would be required to form a curvature over here, and this is what is the origin increase in the strength of the material because of the presence of these sessile dislocations. And let us say you are applying thermal agitation and sufficient stress, then it would lead to the overall the sessile dislocation would also move upward along with the dislocation, but at the same time it will be leaving behind a trail of vacancies. You remember that whenever a climb of edge dislocation takes place, it leaves behind vacancies. There must be vacancies getting formed over here. So, this is the motion, and here you will have, let us say we can describe a radius r. So, we can also say that the radius r which will be formed over here would be given by if tau naught is the stress being applied, then radius of these dislocations would be equal to the alpha GB by tau naught. In all these cases, the steps that we have looked at, what is the length, how much would be the length? The length would be 1 unit length, which is equal to 1 Berger vector. Okay. So, that is jogs so far we have discussed are simple jogs. Now, we will discuss something about what is called as super jogs. So, this is the behavior of a simple jog. Now, how do these super jogs behave? What are these super jogs first of all? So, as you can realize the way we are describing, the super jogs would be something larger in size than a jog, and that is true when more than 1 atomic spacing. So, the jogs would have 1 unit length, meaning 1 atomic spacing, but when you have more than 1 atomic spacing, then it is called super jogs. And there are 3 categories that you can put. First one is when height of few atoms. So, it is more than 1, but still only few atoms spacing. In this particular case, you have something like this screw dislocation, there is a jog which is a little larger than size, and if the whole thing is moving, this will also drag the edge dislocation, however, leaving a trail of vacancies behind. So, this can move. What we are trying to say is that when it is few atoms thick, it can still move, and when it moves, because this is a climb of the edge dislocation, it will leave behind a trail of vacancies. These are the screw dislocation parts. So, and you must realize this is the edge dislocation part, which is few atoms thick. So, if you want, you can even draw so screw dislocation can drag such jogs and creating several vacancies. Intermediate size. So, this is the super jogs. So, super jog size. Now, you can have intermediate size. What is the intermediate size? It is such size that if you look at the dislocation, now here it is the jog, and if you have the 2 of these, then it is not neither too small that it can be dragged, it is sessile, but at the same time it is not so big that there is interaction between the 2. So, the 2 arms keep interacting, and they will, and since they are interacting, it will not overlap to this region. For that overlapping, you will need very large stress, because there is interaction between the 2 arms of the dislocation. So, that is the intermediate size. So, in the intermediate size, 2 arms of dislocations interact. So, that is the important thing, that they interact. It is not too large that they become too far and there is no interaction between them, neither it is too small that it can be dragged, and can pass one another only on application of large stresses. So, this is the second size. Now, you have the even larger size, very large jogs. And what will be the characteristics of this? Based on this, you can realize this one will be obviously very large, but what will be more important is that this arm which is over here will be independent of the other arm. So, it can form anything, any loop like this over here, this one can form any loop like this. So, the other end is free, but this end of this dislocation, it will act like an independent dislocation whose one end is free and the other end is fixed. So, similarly over here this will also act like an independent dislocation where one end is free and the other end is fixed. So, very large jogs, two arms of dislocation move independently and fixed at one end. So, here you can realize that the distance between the two parts, and let me, to make it clear, let me clearly mention that this is the edge dislocation jog. This is the edge dislocation jog. So, this is the jog we are talking about, this is the jog we are talking about, this is the jog we are talking about, and in this particular case the last one that we discussed, very large jogs. This is so large in size that these two parts, the other end of these dislocations, they are independent, they do not feel any stress because of the other side, and therefore, it can form loops or whatever because of the local stresses, because of the effect of local stresses, it can form or take shapes. It does not have to, shape will not be determined by what is going on the other side of the dislocation. So, now that we have looked at these jogs and kinks, it is time to look at some very simple problems. And so far what I showed you was with respect, all the intersection of dislocation was with respect to a drawing. But now let us say you do not have a drawing and I give you just the Berger vector and the line vector, can you interpret these? So, let us look at it. So, in the first case what I will give you is that there are two dislocations obviously, where you have Berger vector equal to, for the one dislocation 0 0 1, and for the second dislocation the Berger vector is 0 1 0. So, now you have to describe the intersection of these edge dislocations. So, assume that this is a edge dislocation and this is a, in fact I do not even need to mention that. Okay, let us for the sake of simplicity, because there are some more information that we can extract. So, let us say that these are two edge dislocations. So, we are given two edge dislocations, one is 0 0 1, another is 0 1 0. So, we are assuming a simple cubic type of system where the slip direction is 0 0 1 and the slip plane is 0 0 1. So, what will be the step in here, and what will be the direction, what will be the magnitude, what will be the character. So, let us look at first in the step in over here. What will be the magnitude of the step over here? It will be equal to 0 0 1, magnitude of this equal to 1 A, and what will be the direction? It will be equal, sorry, I should also write 0 1 0, and the direction should be, because we are talking about Berger vector screw dislocation 1. So, it should be equal to 0 1 0. Similarly, for S2 it should be equal to 0 0 1, magnitude of this, which is equal to 1 A, and direction should be equal to 0 0 1. Now, this is the direction, Berger vector is this, these two are perpendicular, therefore, it will be a edge character. Here this is the direction, this is the Berger vector, these are again perpendicular, therefore, this will be a edge character. So, we do not need to know what is the line direction over here, just by looking at the two Berger vectors we can say that this is how it will look like, and this is what we get in this particular one, and we will try to solve some more examples in the next time that we meet. So, we will end over here.